second session of the day. I'm Brian Patton, the MC of the education track. I'd like to introduce Jim Mccracken, who's an employee of Inmar, does a fascinating thing there, none of which he's going to talk about today. Because the really interesting thing he's going to talk about today is his sort of hobby and passion about 3D manufacturing.
I would say it's absolutely a passion, yeah.
And I put out on the listserv, I have one of the ones that you see outside, and just a beginner at it, I put out the listserv, and Jim said I could come and help. I'm nearby, and so I greatly appreciate him showing up. He and his teammate up there at the table are both furiously trying to prepare actually build one during the conference. So swing by and offer him encouragement, but don't distract him too much because he has to get it done by tomorrow. So I won't chew up any more of his time, but if he seems a little, been up late, we're going to, it's really greatly appreciate it. So Jim, thank you so much.
Thank you, Brian. Can everyone hear me all right? Quick show of hands, who was at the reception last night at ITology? So did you guys get a chance to check out the Open IT Lab? I don't know if you saw, there's a working space at ITology just around the corner across the street from the Capitol building where there's going to be an actual 3D printer permanently ensconced, available to the public for use. I absolutely encourage all of you in the area to go and check it out in a few weeks when it's there and working and so on and so forth. And a lot of the ideas and concepts that we're going to talk about today, you can go to the ITology lab and actually play around with the machine and see how it's going to work. All right, without further ado, let's get started. So I'm going to talk a little bit about Industrial Revolution 1.0 and Industrial Revolution 2.0 and what these terms mean and what it means when we talk about them. We're going to try and breeze through that part real quick. We'll talk about how in the open source world you have kind of software and hardware, and there are similarities and there are differences between them. Then we'll talk about, there's a particular idea that I really like called Woodshop 2.0, and this is particularly relevant to education. How can I enhance woodshop teaching with this technology? And then we'll talk about some other places where it's relevant in the education space. So the Industrial Revolution 1.0 was really kicked off with the invention of interchangeable parts. Eli Whitney's cotton gin, that's the patent application you see there. So he invented a cotton gin, and the big innovation there was that all the parts were the same. If I had two cotton gins and they were both broken, but they were broken with different parts, I could take parts out of both of them and make one working cotton gin. And this really started the idea that I can mass fabricate many, many objects quickly with a particular tool set. And so you see after he gets the US patent, he can make as many cotton gins as he'd like. The tooling was really only good at producing one part in mass. You could have a design for a gear, and you can make a lot of gears, but you couldn't make a water pump or something like that, right? You have a gear-making machine, and it's tooled specifically to making those gears. It doesn't really give you a bespoke manufacturing path where you can customize the pieces for the application as you need them. OPEC decides to reduce oil production to drive up barrel prices. Apple releases multiple versions of the iPhone and iPad, and there's fundamentally the same amount of metal and silicon in them, but they're at vastly different price points. Porsche builds a car that I can pay $1 million for that isn't 100 times better than the car I paid $10,000 for. These are all examples of artificial scarcity, where the manufacturer has to come up with some sort of differentiator in our industrial world to sell their products. When everyone can make the same product cheaply, you have to either, at the low end of the market, drive volume through cost and niche applications, or at the high end, drive it through features. The idea in the Industrial Revolution 2.0 is that you really want to get rid of that idea of artificial scarcity. So, and this is an actual example that happened in the real world. Some guy with a 3D printer decided to make a whistle one day. He was late for coaching practice and he couldn't find his whistle, right? He uploads it to a public open source repository. All of a sudden, within hours, people around the world are downloading and printing out his whistle. Other people are taking it and remixing it. This guy doesn't want a lanyard hook. This one wants it to be very small, and so on and so forth. All of a sudden, you've kind of created this economy of whistles where the more of these things are printed out and redesigned, the more valuable they are. That's really the fundamental idea behind the Industrial Revolution 2.0, is that you're taking that scarcity out of the hands of manufacturers and you're placing it with abundance in the hands of consumers. The first Industrial Revolution was really about standards and conformity. The second revolution is about technological innovation. It's about using that technology to break conformity. The more people that take my thing and print it out, the more people that have it, the more people who are working on it, and therefore the more valuable that thing is. This is exactly the same idea as in open source software, right? If I have many eyes looking at my code, I personally get value from that by bug fixes and things of that nature. So it's based on an economy of openness. You have to have open descriptions of these things. You have to have a public repository where people can easily find the things they're looking for. And it's not just about the software. You have to open source your processes. You have to open source your procedures. You have to open source your firmware, your hardware, even operating in financial transparency. An Industrial Revolution 2.0 company will act in a totally transparent manner because not only are they helping the marketplace in that way, the marketplace can in turn help them. So let's talk a little bit about the difference between software and hardware. In the software world, bits are free, right? I can take a piece of software that's composed of binary code and I can make a perfect copy of it for a few pennies worth of electricity in terms of writing the bytes to the memory, right? And it's probably not even that much. We're talking really fractions of a cent here. So open software can be free as in beer because it doesn't cost the distributor anything to give it to you, or it can be free as in Libre. You know, it's an open design that people can share that you might be charging for or you might not, right? Producers generally earn revenue in this kind of a marketplace through value add services. I'm going to sell you a support contract. I'll sell my programming staff to you to make this feature that you really want integrated into it, and so on and so forth. And as the software gets better, everyone benefits. Open source hardware takes a lot of those same ideas, but you're talking about physical things. Materials cost money no matter which way you slice it. So you'll never see free as in beer open hardware in that unless there's a manufacturer who's willing to sponsor that. You will see free as in Libre because people do want these designs out in the marketplace. They want them to be publicly available. So let's talk we talk a little bit about how open hardware can impact economies and markets worldwide. Let's talk a little bit about the tools you need for it. The first tool, and many people are probably familiar with this tool path, is a subtractive tool path. It's a traditional material working technology. You see this in CNC, you see it in laser cutters and water jets, and all these machines where you put a block of material in it, you give it a design file, you hit go, and it shaves or cuts or removes material to give you the part you're looking for. There are several advantages to CNC, but the biggest disadvantage is it's wasteful from a materials perspective, right? And I have to get my material in block form. I can't give it a thread of wood and have it build a chair. I have to get a piece of wood as big as the chair I want and tell it to shave it down, right? You also have additive tools. That's the MakerBot Thing-O-Matic. That's the tool that will actually be in the Open IT lab when we get done building it tomorrow. By the way, if anyone hasn't seen, we have that workshop tomorrow. I think it's from 9 to 11, is that right? So please come. We're going to try and have it mostly put together, but we absolutely want you guys to get in there, put some pieces together, see how this thing is put together, and then we'll operate it for a little while, depending on our time. That's called fused deposition modeling. Basically, I'm taking a filament of plastic, I'm feeding it through a machine. By the way, this is the RepRap. It's an open source version of the Thing-O-Matic. Interestingly enough, all the white plastic bits you see here were printed on a MakerBot, the first version of the Thing-O-Matic. So it truly is a replicating open source hardware design. If you have the tools, you can make another one and another one and another one. Now, that doesn't include motors and electronics and all these metal bits you see, but we try to find those so that they're from multiple suppliers. There's open hardware descriptions of what it is and what the dimensions of it are, and that way you can source it from whomever has the tools and technology to create it. There's other methods, though, that don't involve extruding liquid plastic onto a bed. You have laser sintering, where you have some kind of powder material, and you heat it up almost to its sintering temperature, and then you use a laser to apply a little bit of extra energy into it. The advantage of laser sintering is it's available for a wide variety of materials: plastics, glasses, metals, ceramics. Anything that is sinterable in a powder form can be done on a laser sintering machine. And then you have paste extrusion, things like plaster and PDMS, aka bathroom caulking. Things like frosting and sugar and all sorts of materials that you wouldn't typically think of as an open hardware idea can be extruded through paste extrusion. And you do see ideas in the marketplace starting to develop for how can we use this both from a hobbyist perspective and from a commercial perspective. Imagine if you had a frosting extruder and a cupcake business. You could easily do custom frosting on every single cupcake. You know, you can put the names of the kids at the birthday party or, you know, something along those lines on every single one individually. And this is really the power of the Industrial Revolution 2.0. You're not locked into one design every time you make a part. PDMS, is anyone here from the biotech fields? Oh, that's a shame. PDMS is used very strongly in the biotech fields to make lab-on-a-chip and other microfluidic devices, so that's why we mentioned it. So how do I get the stuff? Okay, it's great that, you know, I can print out one of these, but I have to have a 3D printer to get that far, right? How do I get it? Well, you can go the open source route. This is that open source RepRap that's mentioned at the top there. You'll see a picture of it. It's got open plans. It's makeable on a 3D printer. It's relatively inexpensive. I'm not going to talk about prices because this is an open source talk, but if you want to come by the booth later, we can talk about how can you personally get access to one of these machines. The really great part about the RepRap is that Ideology is going to have the Thing-O-Matic. So as long as you can acquire the rest of the bits and you can spend a few days on site, you could absolutely print out the plastic pieces you need. Then you have kind of the semi-open commercial route. MakerBot is a great example of this. MakerBot releases all of their design files online. If you have the tools and technology, you could absolutely make a MakerBot without going through MakerBot Industries. In this case, we're talking about having a laser cutter and a large supply of 5mm birch wood. Even better, though, you can just go to MakerBot. They'll do all that for you, send it to you in a kit. You just bolt the thing together. And that's fundamentally what we're going to be doing tomorrow with the Thing-O-Matic. It's relatively inexpensive. It's easy-ish to assemble. One of the really great parts about building from a kit like that is that you will have an intricate knowledge of the mechanics of the bot, so when things go wrong, and they will inevitably go wrong, you'll have the tools to fix it. Then you have commercial suppliers. PP3DP is a relatively inexpensive one in that space. They make something called the Up Printer. Z-Corp, Solido. I've talked to a couple people here who have Dimension printers at their office. Now, that's like a $30,000 printer, and you definitely get what you pay for there, and it's a wonderful machine, but I personally don't have $30,000 to spend on it.